Let's open this conversation up by reminding us that in a situation in which there's an acceleration, we have, for the most part, only dealt with situations in which the acceleration is something regarding the change in speed of an object. All right? And we've been fixated on whether the object sped up or slowed down. So if an object has a velocity that is, say, I don't know, that way, then we've dealt with issues where the acceleration was in the same direction as the velocity, thus making the velocity a bigger number, or was in the opposing direction of the velocity, thus making the velocity a smaller number. In both of those circumstances, we dealt with one-dimensional problems in which the velocity was increased or decreased, speeding up or slowing down. But there's absolutely no reason why you couldn't accelerate in this direction. This acceleration would have the implications of not only changing the speed of the object, because there's clearly a component of that acceleration that opposes the motion of the object, but there's also a component of this acceleration that is perpendicular to the velocity of the object. And this would have the result of causing the object's velocity to change direction. So causing it to turn. Now, we haven't spent any time talking about accelerations that are changing direction or causing an object to change direction. But by definition, any change in velocity is the result of an acceleration. So although these are about changes in speed, there's certainly got to be one that's about changes in direction. Now, there's no reason why you can't be doing both at once. None at all. But luckily in this class, we're going to focus. And we're going to focus on situations in which an object's velocity is either changing size or changing direction. And for the time being, can't say we'll do this all year, but for the time being, we're going to deal with situations in which the object's direction is changing in a uniform way. We're going to deal with circular changes in direction, where an object's traveling in a circular path and therefore its direction is changing in a way that is regular and predictable and has a constant radius of curvature. So if that is a new term for you, please get it into your vocabulary. But we're going to deal with problems that have a constant radius of curvature. I believe the phrasing is pretty obvious, and I shouldn't have to define it, but the radius of curvature would be whatever section of the circle we're dealing with. So just like saying radius of curvature, I think I can probably say that all of these points share the same center of curvature. If there was a full circle, that's where the center would be. Now, this part might not be obvious to you, but an object traveling on a curved path will always have a velocity that is tangent to that path, unless the path is straight, in which case the velocity will be along the path. But if the path curves at any moment, the instantaneous velocity is tangent to that path. Now, if we assume this object has a constant velocity, meaning a constant speed, I said the wrong word. If we assume the object has a constant speed, or how fast it's going isn't changing, then the acceleration acting on this object can only act perpendicular to its velocity. Just following the definitions from geometry, right? So that being true, it should be kind of clear that an object, in order for an object to travel in a curved path, its acceleration is going to have to change direction all the time because the velocity is changing direction all the time. But it's not arbitrary. Is it pretty clear that this object's acceleration would have to point towards the center of curvature? Do you guys see that pretty clearly? Which is why we call this a centripetal acceleration. Centripetal. A centripetal acceleration points towards the center. That's what the word stands for, center pointing acceleration. Now we can't calculate this using something like that. We can't take the difference in the velocity over the time. You can prove where this comes from, but it's not worth the effort. When we're dealing with a centripetal acceleration, I'm going to use an A with a subscript C. For the time being, our problems are all going to be uniform, which means the acceleration is a constant value. So it's changing direction, but the magnitude of it stays the same. Thus, uniform accelerated motion or uniform circular motion. We're dealing with stuff that has a constant centripetal acceleration. To calculate it, it's how fast you're going divided by the radius of curvature. But we square the velocity, which tells you that small changes in velocity require big changes in acceleration. Now, I want to impress upon you something that I think is important here, that if you don't write it down, you might miss the nuance. And that has to do with requirements. If you want to travel this speed and make this tight a turn, this is how much acceleration will be required. You may not have that much acceleration to work from, in which case you will not be able to make the turn. I'm imagining people who are running a red light. It's just turned yellow, they're worried it's about to turn red, and they hit that light and hope to make a left turn before it turns red. Have you ever watched these people? They all kind of do the same thing, speed up real fast just to get into the intersection, then jerk that wheel and turn, and often can't make the actual turn. Right? The law states you're supposed to turn from the leftmost lane to the leftmost lane. You guys know what I'm talking about? You ever watch that person turn from the leftmost lane to the rightmost lane? Sure, they're probably going too fast. And because there's a limited amount of acceleration available, they have to increase their radius of curvature. Right? You see that it takes more acceleration to make a tighter turn. So right now, Citrus Park Boulevard, if you guys, that turn from going south on Sheldon to Citrus Park Boulevard right there, they recently increased it so that there's now 2 left turn lanes there. Well, the people that are on the innermost turn lane have a smaller radius of curvature. They are at a disadvantage than the people that are on the outer turning radius, because they will need more acceleration if they wish to stay at the same speed as the people on the outer turning radius. Of course, you could argue that the people on the outer turning radius are making a bigger circle too, right? So there's that part as well. But these all play together. But be very careful approaching an intersection. It should be clear that if you double your speed, it takes 4 times the amount of acceleration to get you to turn. That square has caught more than one person at Citrus Park Boulevard in a very bad situation. Just look at the curb on the other side of the road, all the way on the right-hand side by that Firestone tires. Look at the curb there. It's covered in black marks for people who didn't make the turn. More importantly, the sign over there is mowed down about once a week from people who didn't make the turn, who hit the light going too fast, attempted to make the turn, and the acceleration required exceeded what the car could provide, and they slid. What's that? Yeah, that's the way you do it. Mm-hmm. Sure. Now, I want to talk a little bit more about this in a slightly more critical light, but I want to first remind us that any problem involving an object traveling in a circular path is going to be a second law problem. It will have to be. The object is accelerating. Therefore, there must be an unbalanced force acting on the object. It's not going to be a new force either. Consider the car that's making a turn over here. Let's take a look at that car from the back because it's kind of hard to draw the forces on the car the way I have it set up there. So I have to draw a car now. Let's see if I can do better than fifth period. We're already off to a bad start. Maybe give it some ears and license plate, maybe tail lights. Does it look like a car now?
It kind of looks like
It looks like a pig, I know. It's so sad. So maybe I'll draw the back window. Does that make it better or worse? So this is like the license plate. Exhaust, okay. Dual exhaust, there we go. So it's really cool.
Why is exhaust in front of the back there?
So it's a car. Just be my friend for a minute. It's a car. Forces that act on the car. Name one.
Normal.
Oh, okay, we'll go with that one. Normal. Normal's going to have to be this way, assuming it's in contact with the ground. It feels like it is. What else? Weight. So we're going to have a downward force. That sounds like a good one right there. So there must be a force to the left on the car. What is it? What causes your car to turn? What's that? Well, I do know that the steering wheel is where we kind of think of it, but that's not a force. I mean, there's not much by way of forces, guys. It's not a new force. It's got to be friction. Friction causes the car to turn. Now, you think that the car just rolls that way. That's not what's happening. In fact, it's not just any friction either here, guys. Static friction. You do not want the tires sliding with respect to the road. You want them not sliding with respect to the road. And think about it. If there's no friction, does the car turn at all? No, it probably doesn't go anywhere either. But when you go to turn your car, you're right. You turn the wheels. So the wheels are at an angle relative to the driving direction of the car. This causes there to be a force on the wheels from friction. Now, part of that force does act to try and slow the car down, so you have to drive the car forward. But the other part of that is a force that acts against the wheels to make the front part of the car move to the side. If the front car goes, the back part follows. And yes, there are cars, of course, that have rear steering, but they're few and far between. But that's what makes your car turn. Bicycles, motorcycles, even more complicated. How many of you have ridden a bicycle sometime in your life? So, you know why training wheels are so terrible? They don't let you lean into the turn. And that's what the bike naturally does. If you don't lean and try and turn the turn the handlebars of your bicycle, you'll just fall over. There's a reason why you have to lean when you turn on a bicycle. Motorcycles are the same way. Now, just looking at this, is it clear that one of the forces is unbalanced?
Yes.
And that it's in the direction of the turn? So before we get away from this particular example, we would draw a coordinate system, and we'd want the x direction, or one of the directions, to be in the direction of the acceleration, and we'd want that to be the positive direction. The other one, by necessity, will be up and down and hopefully be zero, because you're designing it this way. And when I do that, I'm saying that the net force in the x direction equals MAC. Right? I'm telling myself by putting the C there that we're talking about an unbalanced force that causes a centripetal acceleration. I'm never going to say that there's a centripetal force. There isn't one. There's an unbalanced force that causes a centripetal acceleration. In this case, the only force that's acting in that direction is friction. So friction is causing the centripetal acceleration. In fact, I can probably do a few things here when it comes to substitution. So suddenly our problem can be about how fast the car is going and how tight the turn is, even if you think it's a force problem. While at the same time, net force in the y direction equals 0. So normal equals weight. Same analysis we've been doing. And now you can take that, add it to the information we know about how static friction works, and suddenly you have a way of relating parameters for a turn. This tells you, if you know what the coefficient of friction is between your tires and the ground, it gives you a reasonable way to figure out what the maximum velocity you can make the turn at. Right? You see that, don't you? You start putting those things in, you're going to get velocity as a function of the coefficient of static friction. Stay below a certain speed and you'll be fine. Go above that speed, you're in trouble. And then that leads to what you can probably start to do in more complex situations, like banking the turn, to help with this process. So we're just scratching the surface, but I want to say this problem is in your homework. There it is, worked out. Yeah, there's probably numbers involved. Let's take a look at another one. I was a little disappointed in talking with this in fifth period, because they're unwilling to get behind this. So we are hopefully, although the paperwork got sent back to me for Busch Gardens because I needed Mr. Narkter's signature and took it to go to him, and he's not here today. So that'll put it off another day. Have you ridden Scorpion? Scorpion's an old school ride, and at the time that Scorpion was installed in Busch Gardens in the 80s, it was a cookie cutter roller coaster. It was when I say that, I mean it was mass produced. Any flat surface could have it constructed on it. Most of the other coasters at Busch Gardens are custom coasters, meaning they're designed specifically for Busch Gardens and only exist at that park. But the Scorpion wasn't. In fact, there's another version of the Scorpion that's as part of a carnival, travels around Africa. Was the last place I think it was around. I bring up roller coasters because roller coasters are about manipulating what you feel, and all carnival rides do so. So if you look at a simple lift hill to loop ride, the Scorpion is the only ride in the park that has a regular 360-degree loop. All the other loops in the park aren't 360 unless you count that horrible, horrible Tigress ride, which is just, I can't stand it. For those of you who like it, good on you. I can't stand it. But I want to talk a little bit about what happens when the cars make it to the top of the hill and go across the top of the hill versus what happens when the cars make it to the bottom of the hill and go around the bottom of the hill. Because in either case, a portion of the route is circular. It doesn't have to be an entire route. Remember, when we're dealing with uniform circular motion, you only have to be traveling in a circle for a small moment. So although I want to relate this to roller coasters, let's just talk about a kind of a simple road surface where there might be a dip in the road, followed immediately by, say, a hill in the road. Something like that. Is that okay? Now, in this example, we're looking from the side as a car, maybe your car, approaches both the dip and the hill. When the car travels into the area where there's a dip, it's traveling in circular motion. We tend to think of circular motion being when the car turns, but this is a circular motion problem too, isn't it? Isn't the car traversing a circular path? The radius of curvature would now be considered something like this for the radius of curvature. In the same way that there's a radius of curvature over here. Again, similar, but from the other side. For the car to make it through the dip in the road, the forces will have to be unbalanced. If they're not, the car can only travel in a straight line. And I don't really think you want to burrow through the ground. So in order to get out of the dip and maintain your speed, there will have to be an unbalanced force acting on the car. What forces are acting on the car at the bottom of the dip? Weight for sure. In fact, we know if the car continues to travel and successfully makes it out of the dip, the car's going to eventually make it to the top. Oops, don't want to do that. The car's going to eventually make it to the top of the hill. We hope at least. Where here, the car will also have the same weight. Will the weight have changed substantially between these two places? I hope not. Maybe chucked one of you guys out of the car. Well, if we want to travel in a circular path when we're at the bottom of that dip, oh my word, you gotta be kidding me. What happened there? Well, I think we've got a little something going on there. So let me fix that. There we go. Yeah, you make mistakes. So there we go. Now, what must be providing this upward force? Normal force. So in a situation where you're about to go through a dip, the only way you do so is if the normal force exceeds the weight. So normal minus weight equals MA. If you've ever gone in a dip in a road, you felt heavy. You feel yourself bouncing into the bottom of the seat, being pushed into the seat. Is that a familiar sensation? That's not accidental. That's an increase in the normal force required to push you out into the circle. So you feel for a moment heavier. That's why roller coasters do it, to manipulate you. At the bottom of that first lift hill, you get to the top and you go down. The moment you start pulling out straight and going into the other events of the ride, you feel heavier at the bottom of that ride. Because for a few moments, you are in circular motion. The top's got to be the opposite of this, though. You realize that, right? When you're at the top of the hill, the only way you continue to travel in this circular path is if the normal force is less than the weight. Again, not by accident, but now I'm going to make downwards positive because I want to make the direction of the acceleration positive, which will mean weight minus normal equals MAC. Or in the case of this one, normal equals mg minus mv squared over r. Now, you might not see the implications here, but I hope some of you do. That minus sign could pose a problem, right? If I'm trying to figure out what I experience when I'm in the car, then I'm interested in the normal force. The normal force is going to be less, which is why when you go over a hill, you feel lighter for a little bit, like you're thrown upwards into the car. It's like the car's is moving downwards and it isn't taking you with it. Well, that's because gravity is the thing that has to pull you down with the car. So that's why you feel lighter over the top of a hill. But keep in mind, there's some limits here. Can the road pull downwards on the car? No, normal force only pushes. It can't pull downwards. Now, if you're in a roller coaster, you could do it. The roller coaster wheels are attached to the track, so you could pull downwards on the car. You better be attached to the car, should that be the case. I'm finding fewer and fewer people have ridden the old version of Gwazi. Is there anybody here who rode the old version? It's a pretty rough ride. But it had several places where the normal force approached zero. Right? Now, you do understand, if the normal force approaches zero, you lose contact with the seat. Right? It's no longer touching you. In fact, you can figure out from this what velocity you would lose contact with the seat. Do you see that? All right, just set that equal to zero and find out that speed. So the truth is, we tend to want to feel the seat underneath us. It makes us feel a little bit safer. Most ride designs are designed to make you feel the seat there, which is why they generally don't go over hills like this very much. You'll notice most of your roller coasters don't do that at all. They want to flip you upside down, sure, but they generally want to keep you in the car seat, so they want you feeling the seat. Don't get me wrong, going upside down on a roller coaster poses the same kinds of problems. You have to be going fast enough to experience a normal force. If not, you fall out of the seat. So if we talk about a loop, a roller coaster attraction, where the track has a full inversion, if you're approaching that inversion, gaining speed, eventually you'll make it to the top of that track, right? You'll have to have a velocity this way. It can't be zero. If you stop there, you've got big problems. Consider the directions of the forces now. There's two, I think, right? What's one? So weight's going to clearly be downwards. What else? Normal's going to be downwards too. Now, if you're dealing with a roller coaster that can clamp onto the track, that's one thing. But I've got some demos in the back where it's just a marble going down a track. If you want the marble to make it all the way around the track, you've got to make sure you have enough velocity to go through this track. If this is weight, and this is normal, but in this case, weight plus normal equals MAC. So weight plus normal equals mv squared over r. There is a finite minimum speed that must be maintained, or else you got trouble, right? You need to have a bit of a normal force. When the normal force goes to zero, you're losing contact with the track. That means you have less force than you need to make this turn. And that means your turn is going to be smaller. Right? That's what's going to have to happen. So when we deal with these kinds of discussions, there are limits that have to be maintained. This is the amount of acceleration you may have to work with. It looks like the limits for the acceleration here is when the acceleration approaches g, right? That would be a limit. Now, the other side of that is you're always fighting inertia. That's a big part of this. What keeps you on a track is inertia, the fact that your inertia wants to go in this path. Wants to. It resists changes in motion. There needs to be a force to change the direction of your motion. How about this, though? Who's been on one of these? Let's see. Horsey number 1, horsey number 2, carousel. There has to be a time when your parents were just done with you and said, here, go ride the horses. We'll sit on this bench here and just watch. And I know that's been some of your experience. Let's say that this is kid 1 and this is kid 2. Now, if the parent's sitting on the bench there, would you guys agree that the kids make it back around at the same time? I mean, does kid 2 make it there first or kid 1 make it there first? Which kid's traveling faster on this ride, kid 1 or kid 2? We sure?
Yes.
Oh, that's good because they were not sure in other classes today, which was making me very concerned. Could be. I am going to explain something, though. Kid 2 is clearly traveling in a bigger circle than kid 1. Agreed? And that's easy and obvious to see. So with that being stated, the velocity of kid 2 would largely depend on the size of that circle. So if I say that this is radius 1 and this is radius 2, then kid 2's velocity would be whatever 2 pi r2 is divided by the time it takes to go around. And the speed of kid 1 is similar. Bless you. Bless you again. So these would be considered their linear velocities, in that kid 2 has linear velocity v2 and kid 1 has linear velocity v1. I could base it on the circle, assuming right now that the circle has some kind of uniform angular speed. So these are linear speeds. But the whole merry-go-round has a single angular speed. We use a different symbol for angular speed, as you might expect, but we also use units that you're probably familiar with, like RPM. What is that? Rotations per minute, RPS. So rotations per second. That doesn't have to be the only way. Those would be based on rotations or revolutions, right? So if I say it takes 4 seconds for the carousel to make 1 revolution, do you all agree that the speed of the carousel would be 1 rotation per 4 seconds, or 0.25 RPS?
Yes.
Can you figure out how many RPM that is? Do you know how to do conversions? I hope so. My experience has been mixed with that. So practice tonight. See if you can. The answer is 15, but see if you have a way that does it regularly, evenly, all the time. Of course, there's other ways to talk about angular speed as well. There's no reason why we couldn't do degrees per second, although we won't. But we will do radians per second. Now, before I close in on this for a minute, how many radians are in 1 complete rotation?
2 pi.
Good. So if I wanted a section of an arc, how would I calculate the length of a section of an arc? Do you guys know? Do you have a formula for calculating arc length?
2 pi r over the angle.
2 pi r over the angle. I don't think so.
Or times the angle over 2 pi.
Okay, so there has been this, people who say basically what percentage of the circle do you have, and find the arc length that way. Some people told me that earlier today. So, and that would be any ratio using any measure, half a circle or 30 degrees over 360 degrees, or, like you said, 1/6 of pi over 2 pi, something like that. However, I thought you guys had been taught this, and it seems like that's not true, that the length of the arc is equal to how much angle you want of your arc times the radius, as long as this is measured in radians. But that doesn't seem like it's something that's been taught much. The circumference formula should kind of be an obvious, lightning rod for this, that the entire length of a circle is, when you go around the entire circle, 2 pi radians times the radius. Now, if I'm dealing with something that has a constant speed, where this is happening in a regular way, then the linear speed would be equal to, this is the symbol I want you to use, Greek letter omega, it's a fancy W, times r, where you can convert from an angular speed in radians per second to a linear speed in hopefully meters per second by just multiplying by the radius. All right.